We also need to be able to determine where the load on the supporting members goes. We call that load path. If a supporting member is itself supported by columns at both ends, the loading goes from that member to the columns. Beam A1, A2 is an example of this. But some members are supported by other members. Beam B1, B2 in this floor system is an example. This beam is supported by girders A1, C1 and A2, C2. The load from beam B1, B2 goes to the girders, which then carry the load to the columns. If we draw the idealized beam B1, B2 as simply supported, the loading is trapezoidal because it supports a triangular region from the left and a rectangular region from the right. We see that the girders must apply upward force to keep the beam in equilibrium, so the girders act as the supports. Newton's third law tells us that if the girders push up on the ends of the beam, then the ends of the beam push down on the girders. That means the load from beam B1, B2 becomes point forces on the two girders. Let's draw the idealized load for girder A1, C1. From A to B, we have a trapezoidal distributed load, and from B to C, there is no distributed load since the panel is acting one way in the other direction. But at B, we have a point load from beam B1, B2. If we miss the point load, we will significantly underpredict the effect on the girder. Sometimes the framing plan has members carrying members carrying members. It's not always obvious which is the supporting member and which member is being supported. One way to figure out the load path sequence is to think in terms of construction sequence. The columns go in first, then the members that attach to the columns. Then we add members that attach to those, and we add members that attach to those new members. And this process can keep going until we are ready to add the diaphragm itself. Load travels in the reverse sequence. It starts on the members and ends up in the columns. To figure out load path, I recommend the following process. As you look at the framing plan for the diaphragm, identify all members that attach only to columns. Label these number 1. By the way, these would include members cantilevered out from a column. So if the member requires a rigid connection to the column in order to stay up, it is also labeled number 1. In this example framing plan, if we don't have rigid connections at B3 and B2, this panel folds down. So these two members are also labeled number 1. Next, identify members that attach to a number 1 member at least one end. The other end can be attached to a column or another number 1 member. Label these number 2. In our example, this member is connected at both ends to members labeled number 1, so it is clearly a number 2. This member connects to a number 1 on the one end, but to a column on the other end. It is still labeled number 2, as is this one. Now we look for any members that are not labeled and attach at least one end to a member labeled number 2. Label these number 3. In this example, there is 1. The load path through the supporting members is the reverse. We start by drawing the idealized loading on the highest numbered members, number 3 in our example. We calculate the reactions, and those reactions become point forces on the next members. So for this example, we would draw members C2, C3, and D2, D3 next, since they are labeled number 2. Member C2, C3 gets triangular loading from the panel on its left, and a point load from member C2.9, D2.9. With this idealization, we could calculate the reactions. Member D2D3 gets trapezoidal distributed load from the panel to its right, and the point load from member C2.9, D2.9, and we would calculate the reactions holding it up. Member A2A3 is also labeled number 2, so we would draw that one and calculate its reactions as well. Once we have all the reactions for the members labeled number 2, we can draw the idealized loading on the members labeled number 1. Let's pick member B2D2 to illustrate. This member supports a rectangular region from the column line 1 side and a trapezoidal region from the column line 3 side. Then we add in the point load from the C2 end of member C2C3. The reactions we calculate for this member are point forces added to the supporting columns. We would continue this process for all of the members labeled number 1.